Welcome to the Introduction to Stream Morphology and Critical Concepts for Aquatic AIM. This video gives an overview of general critical concepts needed to understand the Aquatic AIM Protocol. Further guidance on these concepts and many of the terms discussed in this video are in the field protocol starting on page 81, Appendix B in the glossary. The first part of this video discusses types of aquatic ecosystems, focusing on streams and common factors influencing the shape or morphology of streams, such as slope, discharge, and position in the landscape. Then it covers common stream channel concepts used during implementation of the Aquatic AIM Protocol and are critical to understanding aquatic AIM data such as Bankfull. The BLM monitors the health of two types of freshwater surface systems, Lentic and Lotic. Lentic systems are defined areas that support riparian vegetation and often have surface water, but do not have enough flowing water or energy to form a channel. These are systems such as lakes, wetlands, and meadows. Lotic systems contain flowing water with enough energy to form a defined channel and transport sediment, such as streams and rivers. The Aquatic AIM Protocol covered in these videos, TR 1735-2, is focused on sampling wadeable Lotic systems. For more information on how to sample other systems, such as Lentic or those that require a boat, please contact the National AIM team. The Lotic AIM Protocol uses a combination of GIS layers and field assessments to determine flow permanence. In the field, streams must have water present at 5 of 11 main transects to be sampled. The Lotic AIM Protocol is primarily designed to assess the condition of perennial streams. Perennial streams have a flow or discharge pattern that is continuous on an annual basis, while intermittent and ephemeral streams do not flow as often and therefore can have different physical characteristics and ecology. Intermittent streams have flowing water during the wet season or following spring snowmelt. These stream channels may not be as well defined as those observed for perennial systems, but erosional and depositional features must be present. Ephemeral streams have less frequent flow than intermittent streams and only flow in response to precipitation events. Ephemeral streams do not have identifiable erosional or depositional features. In many cases, there may be upland vegetation within the stream channel. In addition to classifying streams by flow permanence, it can also be helpful to think about streams relative to their position in a watershed. Headwater mountain streams have very different characteristics than streams that drain lower elevation shrublands, grasslands, or deserts. Many BLM districts contain a combination of these ecosystems. Keeping this watershed context in mind is critical for identifying stream morphology features and interpreting aquatic AIM data. Some of the biggest factors influencing stream morphology at the watershed scale are stream slope, watershed area, and the amount of flow or discharge. In general, these factors vary in a predictable pattern throughout watersheds from mountain headwaters to basin outlets, with mountain headwater streams having steeper slopes, smaller watershed areas, and lower discharge. Stream order is a measure of the position of a stream reach within a watershed, which tends to correlate with the spatial patterns of stream slope, watershed area, and discharge from headwaters to basin outlets. Aquatic AIM sample designs commonly use Strahler stream order to organize Lotic systems into 3 size class categories: small streams, which are first and second order, large streams, which are third and fourth order, and rivers, which are fifth order. Again, smaller stream orders have fewer tributaries and tend to have steeper slopes, smaller watersheds, smaller channels, and lower discharge than larger stream orders. The water in streams can come from various sources, including precipitation, such as snow and rain, or from groundwater, like springs, or a combination of these. The exact origin, the timing of inflow, and the proportion of inputs from each source determines the hydrology of a system. For example, spring-fed systems tend to have more stable flows than systems reliant on direct precipitation. The climate, topography, and geology of a watershed has a large impact on a stream's characteristics, including its size and flow patterns. For example, on the left is a hydrograph, a graph showing discharge patterns through time of the Logan River near Logan, Utah, and on the right is a hydrograph of the Virgin River near Hurricane, Utah. The Logan River is primarily sourced from snowmelt from the surrounding high elevation mountains, which tends to yield the most water during the late spring and early summer during snowmelt. This accounts for the large spike in the graph in May and June, and for the lower flows the rest of the year. The Virgin River is not located next to high elevation mountains, like that of the Logan River, and primarily relies on rain events and groundwater for its flow. This accounts for the continuous spikes in the graph, which are responses to major rain events during summer monsoons. In summary, the climate, topography, and geology of watersheds influences the hydrology and morphology of streams. Flow amount and timing, combined with stream morphology, are two key factors influencing in-stream and riparian habitat. We will now look at stream morphology at a more local scale and discuss common parts of streams and the critical features that are measured during aquatic AIM sampling. Aquatic AIM assesses stream morphology along a length of a stream called a reach. Reaches are scaled to the size of the stream so that they capture numerous replicates of common habitat features, such as pools and riffles. Pools are depressions in the stream bed that are laterally and longitudinally concave, bound by a head crest and a pool tail. Pools tend to have deeper water and provide habitat for various fish species. Riffles are lengths of the stream that are steeper, shallower, and dominated by coarse substrate particles and faster velocities compared to pools at base flow. Riffles are important because they provide good habitat for macroinvertebrates and other organisms living in the stream, requiring well-oxygenated water and substrates with low amounts of fine sediment. Within each sample reach, there are several critical features that must be clearly identified before the sampling process begins. These critical features are Bankfull, the elevation at which the stream just starts to overtop its banks; Floodplain, the flat depositional area at or above Bankfull; Scour, which defines the active channel; Thalweg, the deepest place in the channel with the most flow; and side channels, which are any additional channels besides the main channel. We will discuss each concept in more detail in the following slides. When identifying these features, it is important to keep track of which bank each feature is located. The Aquatic AIM Protocol defines size of the banks relative to the direction of the flow of water. Therefore, left and right bank will always be determined when facing downstream. Bankfull is the height and width on the stream bank at which the stream fills the channel and begins to overflow onto the active floodplain. Bankfull height is determined by the water height that corresponds with channel forming flow, which occurs on average every 1.5 years. Bankfull is the most important concept to identify correctly throughout a sample reach. The length of the sample reach is determined from Bankfull width. It is also used as a starting point for many other measurements taken throughout the sample reach. Bankfull height and width is identified and measured on both left and right bank throughout a sample reach. Bankfull is at a relatively consistent elevation in stream and river systems, and will occur at about the same elevation throughout a reach. There are several characteristics that can be used to correctly identify Bankfull, and they are located on page 9 in the TR 1735-2 Field Protocol. These characteristics are a change in bank slope, a change in substrate size, a change in vegetation, the top of gravel bars, and the scouring or staining of rocks. It is important to note that not all of these characteristics will be present at every stream, and a combination of these clues should be used to correctly identify Bankfull throughout the sample reach. Another way to estimate Bankfull height is to use data from USGS gauges. This method is only available where consistent gauge data are present, but can be very useful where data exists. Before data are taken in the field, Bankfull height can be determined in the office on the USGS website at waterdata.usgs.gov by calculating the discharge with a reoccurrence interval of 1.5 years. Then, a regional rating curve can be created on the USGS website by plugging in the gauge number to generate a curve that relates discharge to gauge height. This height can then be used as a reference point when in the field to look for Bankfull indicators. You can find more information on this process at this web address. The floodplain is a relatively flat depositional surface adjacent to a stream or river that is formed by periodic flooding. Floodplains are important because they support riparian ecosystems, provide critical habitat for aquatic dependent species, and dissipate flow and energy during high flow events. Floodplains are always located at or above the height of Bankfull. Some streams will naturally lack a floodplain, specifically streams in V-shaped valleys, which do not have the potential for developing a floodplain. Multiple flat depositional features may exist at a site. These can be active or abandoned floodplains. Only the first flat depositional feature at or above Bankfull is measured, regardless if this is an active or abandoned floodplain. Additionally, if floodplain height differs on either side of the stream, only the lower of the two features is measured. This is because the lower surface will be inundated first during a flood event. The active channel is defined by a scour line. Scour line is the water height corresponding with average annual flow in a Lotic system. Identifying scour line correctly is important because it is used to delineate the extent of several measurements that are taken throughout a reach. When sampling a stream, scour may be located above, at, or below the current water level. Scour line should be evaluated in a straight section of the stream. Scour is always below Bankfull and is relatively consistent throughout the reach. Thalweg is the longitudinal path connecting the deepest parts of the stream channel and is used in measuring the heterogeneity of the streambed's morphology. Thalweg is identified by the location laterally across the stream that has the deepest and fastest moving water. The Thalweg is a continuous feature throughout a sample reach. In meandering systems, the Thalweg alternates between left and right bank. In riffles, where the Thalweg crosses from left to right bank or vice versa, the Thalweg is usually found in the center of the riffle. The final critical concept covered in this video are side channels. Many streams have multiple channels. These side channels create important habitat complexity. The Aquatic AIM Protocol requires sampling the main channel and one additional side channel if one or more is present. Side channels must be separated from the main channel by an island rather than a mid-channel bar in order to count as a separate channel. Islands are stream sediment deposits that have an elevation above Bankfull and are usually vegetated with perennial woody vegetation. Mid-channel bars are also stream sediment deposits that have an elevation above the baseflow water level but are below the Bankfull elevation. Mid-channel bars are almost always unvegetated. If you would like to learn more about identification of these features and how they explicitly relate to the protocol, please watch the Critical Concepts video that is intended to prepare those collecting aquatic AIM data in the field.